Okay. Another one of these problems like we did yesterday, and we'll stop here in a second and actually try the ones off your homework. I meant to have somebody work those. Bless you. So let's again remind you, g of x, on this problem, g of x is equal to 2x minus 3. You can go back and check on your homework to make sure you did these right. G of x is 2x minus 3. That's given to you in the problem. You're not using f of x at all. G of x plus h, because we're asked to find what is g of x plus h minus g of x. Here's g of x. Let's find g of x plus h. Again, all you do is what's in parentheses here. Okay, you're simply plugging into g of x. So instead of 2x minus 3, you have 2 times x plus h minus 3. Take out the x, put in x plus h. That's all you have to do to find g of x, or g of x plus h. Distributive property gives you 2x plus 2h minus 3. Done with that part. So now we're asked to find g of x plus h minus g of x. Just subtract those two things and you're finished. G of x plus h is 2x plus 2h minus 3 minus, make sure you subtract the whole thing, 2x minus 3. If you do these correctly, I'll go ahead and tell you, if you do these correctly, this whole second parentheses should cancel. 2x minus 2x. Negative 3 minus negative 3 leaves you with simply 2h. Next objective, students will find the average rate of change between 2 points and then define it in terms of a difference quotient. Average rate of change. And here's your definition for an average rate of change. And this definition hopefully will look somewhat familiar. If these 2 points are 2 ordered pairs of a function, and you notice here, if x1, y1, x2, y2 are 2 points that are on a graph, we define the average rate of change. And this is very important. We define the average rate of change of a function as x varies from x1 to x2 as the change in the y-coordinates divided by the change in the x-coordinates, or that's known as delta y over delta x, or y2 minus y1 over x2 minus x1, which is your what formula? That's simply slope. So if you want to remember it like this, an average rate of change is simply equal to the slope of a secant line. A secant line is a line that passes through a graph at 2 different points. Notice here our blue line is a secant line, and if we want to find out on average, here, let me explain what average rate of change is, guys. From here to here, my y values change how much? From first dot to second dot, my y values change from 1 to 9, so how much does my y values change? A total of 8. Makes sense? How much do my x values change? 2. So here's what an average rate of change is. For every 8 that my y's change, my x's change 2. So on average, for every 4 that I have in change of y, my x's change 1. So do you see why average rate of change and slope is the same thing? Okay. But here's the thing. We're not finding slope of our graph. We're finding slope of this secant line that passes through our graph. But according to our graph, on my red graph, again, for every 2 that my x's change, my y's change 8, which on average is a change of 4 to 1. It's kind of like a ratio. Average rate of change, remember that. The population of California was 29.8 million in 1990 and 33.9 million in 2000. Do you think that population change is a linear change? I would say not. because there's so many things that affect population. It's not going to grow steadily at the same. Anytime I say linear, you have a steady growth. And the growth from here to here is identical as the growth from here to here. Okay, it's the same rate of change. It's the same growth rate. Um, that's not going to be linear. Okay, population growth might look something like this, right? You might have ups, downs. It might stay constant for a while, but population change is not linear. However, what we're looking for, we can use a linear situation to find the answer. Population of California was 29.8 million in 1990 and 33.9 million in 2000. We want to know the average rate of change. Anytime you see those words, average rate of change, you're looking for a slope. So y2 minus y1, actually, my inputs there would be my years, because in 1990, if you input 1990, you're going to get a population of 29.8 million. And in the year 2000, bless you, you're going to get a population of 33.9 million. Y2 minus Y1, somebody please subtract that for me. Well, it's pretty easy. It's 4.1, right? Subtract 9 minus 8 and then 33 minus 29. 2000 minus 1990 is 10 years. So 4.1 mil per 10 years. Again, guys, all this says is over the course of 10 years, your population grew 4.1 million. That's it. Okay. Slope, though, guys, slope is a rate. 4.1 million people over the course of 10 years. And if you want to divide that, I believe that'd be 0.41 million per year. If I ask you what your average is in science and you told me 91, does that mean that you made a 91 on every test and every homework assignment, everything that you did? No. That's not what an average is. An average is kind of like a combination of all those scores divided by how many there were, correct? Same thing here. If I ask you from 1990 to 2000 how much the population grew each year, and you told me 0.41 million, I'm not expecting 41, what would that be, 0.41, it'd be 410,000. I wouldn't expect that it grew 410,000 every year exactly. But again, that's on average. Maybe it grew 0.42 one year, maybe it grew 0.40 the next year. But on average, over the course of those 10 years, it grew 0.41 million. And again, notice I did put starting calculus. For those of you that are with me in calculus, your very first chapter is this stuff again in calculus. Starting calculus, an average rate of change, also known as difference quotient. The difference quotient is the expression f of x plus h minus f of x all over h. Notice the top is what I pointed out as being so important yesterday. The difference quotient, and you can put that on your formula sheet if you'd like. The difference quotient is defined as the expression f of x plus h minus f of x all over h. Okay, here we go. First problem. Find and simplify the difference quotient for each of the following functions. We will start with j of x here. And again, that j, that's simply a function name. It could be j, k, l, m, n, o, p, any letter there, except for maybe x. That'd be confusing to have x of x. That's x was capital. In order to do this, again, f of x, to find the difference quotient, we'll call it the dq to make you want some ice cream. We'll say instead of f of x plus h, we've got j's here. So j of x plus h minus j of x all divided by h. I know what j of x is. It's given to me. It's 3x plus 2. My next step is I would go ahead and find j of x plus h, which would be 3 parentheses x plus h plus 2. Again, in order to find j of x plus h or f of x plus h, simply take out the x, put in x plus h. We can clean that one up. That'd be 3x plus 3h plus 2. Next step now. In my formula, it says find j of x plus h minus j of x, and then we'll take our answer and divide by h. So let's go ahead and do j of x plus h minus j of x, and we'll take our answer and divide it by h. That is the difference quotient. We'll clean it up in just a second, but again, your difference quotient is equal to f of x plus h, which is here, minus f of x, which is here, all divided by h. Now again, the rest is just clean up. If you did it correctly, these should cancel, 3x minus 3x and 2 minus 2. Leaves me with simply 3h over h. Last step, h's cancel and leaves me with 3. Let's go back and remind you. A difference quotient is an average rate of change. Normally you won't get just a number here. There's a reason you just got a number. Go back to this last problem we looked at a while ago. An average rate of change is, again, how much your y changes with respect to x. For every so many that my y changes on this graph, my x changes this many. Well, really, it all depends on what points you pick. Let me clean this up some. On this graph, we had this point and this point. Okay, so that secant graph or that secant line had a slope of, I can't even remember now what it was. Was it 4? Yeah. But what if I'd picked this point and this point? The change in y with respect to x wouldn't have been the same. Because here my y value would change 1, my x value would change 1, and that would only be a slope of 1. That has a different slant than this blue secant line up here. So if you have a funny shaped graph like a parabola, your graph, or excuse me, your slope of your secant line could change all depending on what 2 points that you pick. And again, the slope of that secant is the average rate of change from this point to this point. Now look at the problem we were working. Somebody share something with me. What kind of graph is that? It's a line. Good. So anytime you have a line, the rate of change from here to here, or the slant of that secant line. Now, how do you draw a secant line? If you've got a line and I say take 2 points and draw a secant line, is that secant line not the same thing as that line? So the rate of change or the slope from this point to this point would be the same slope as it is from this point to this point. It's not like a parabola. It doesn't vary. It doesn't change. What is the rate of change? What is the slope of this line? It's right there. So did we actually have to go through all of that process to find the average rate of change for a line? No. Anytime you have a line, the average rate of change, I believe, is right there, guys. It's called the slope. Right? The slope of any secant line will be 3. So if you're dealing with a linear graph, just look at your slope. Okay. This is not a line. X squared minus 2x. Actually, since I've got this pulled up, let's go ahead and graph this. X squared minus 2x and here you see the graph of it. And again, all depending on what 2 values I choose, you're going to have different rates of change. Like from here to here would be a different rate of change. Look at this. From x equals 0 to x equals 2, you would actually have 0 change. Correct? Does that make sense? Look at this value. Look at this value. My y has changed 0 with respect to x. So your secant graph or your secant line would have a slope of 0 between those 2 points because there is no y change. Okay. So back to this. Let's actually solve it though. Here's f of x. Let's find f of x plus h because we're asked to find the difference quotient. Now this is kind of nasty. Plug in x plus h everywhere you have an x. So instead of x squared minus 2x, you'll have x plus h squared minus 2 times x plus h. So hopefully that answers some of your questions. Where do I plug it in? Everywhere there's an x, not just the first x, not just the second x. Go ahead and get used to squaring x plus h. You're going to do it a lot. And make sure that when you do square it, don't just square each piece. There's a plus sign in between. I believe I said that before. Anytime there's a plus sign in between, you must FOIL it out. I've done it so much, I know for a fact it is x squared plus 2xh plus h squared. Minus 2 times x minus 2 times h. There is f of x plus h. Nothing combines. The difference quotient formula says to find f of x plus h minus f of x all over h. Here is the value of f of x plus h. Let's plug all that in. F of x plus h which is ugly, minus f of x, which is our original problem, x squared minus 2x, which again should all cancel if you work it correctly, all divided by h. Any questions thus far? X squared minus x squared. Negative 2x minus negative 2x. Leaves you with 2xh plus h squared minus 2h. Another way to check yourself is on this type problem, number one, that whole f of x should cancel out if you worked it correctly. Number two, you're going to have to divide by h, and what you're left with should all be divisible by h. It should clean up like that every time. Your last test had a problem very similar to this. You had a trinomial or binomial, I can't remember what it was, divided by a monomial. And some people are asking me, well, how do you do synthetic division with that? This is not a synthetic division problem. This is a distributive property problem. You're going to take all three of these terms, divide by h, and divide by h. When you divide 2xh, and if you need to split it 3 times and put an h for each of these, and create 3 separate fractions, if you need to show that step, that's fine. But 2xh all divided by h is canceled. H squared over h leaves you with 1h on top, and then h over h, again, h is all canceled. Final answer, 2x plus h minus 2. Which really means not a whole lot to us. We have no idea what that means, but I'll explain. Okay, here we go. Explain to you what this means. This difference quotient formula, and try just to listen to this next part, and then we can go back, and if there's anything you need to copy down, I'll give you some time. I just want you to listen to this part. This difference quotient formula, let me explain where this comes from. y2 minus y1 over x2 minus x1 is the exact same thing as f of x plus h minus f of x all over h. And you're sitting there thinking, no, it's not. It looks nothing alike. It's not the same thing. I promise it is. Here's what you're actually doing. Here's where that formula comes from. Let's start with a line because it's a little bit easier to understand maybe on a line. Let's say that there's your line, this is your xy axis, and you're wanting to find the slope, so you're using 2 points on this line. This is your point x1, y1. This is your point x2, y2. Okay, with this formula, what we've actually done is we said, you know what? Instead of doing x2 minus x1, let's let h be the distance from x1 over to x2. Let's let this distance right here be h. Okay. Well, how do you find distance? You take your x2 and you subtract minus x1, right? That's the distance from x1 over to x2. So let's redefine the top as well. So now x2 minus x1, that distance we're going to let be our h. y2. Well, how do you find y2? You plug in x2, right? Well, how do you find y1? You plug in x1. Does that make sense? Y1 is a function of x1. When you plug in x1, you get y1. When you plug in x2, you get y2. So this top, let's rewrite it as well. Instead of y2, let's write that as f of x2. And instead of y1, let's write that as f of x1. Because that's what y2 and y1 are. Is the y values you get when you plug in this x2 and y, or x2 and x1. Let's clean it up just a little bit more. Okay, we're gonna allow this to happen. We're gonna this is how we're gonna set our graph. We're gonna say this first x here. This is gonna be like a starting x. Instead of x1, we're just gonna let that be our original x. And this x2. Think about it. x2 is located here. x2 is simply this first x plus whatever that distance was, is it not? So how do I get from x, what used to be x1, over to x2? I add this h value. I add that difference to it. So they've rewritten this formula as, instead of f of x2, they said f of the original x here plus whatever that distance was, minus that original x, that first x. And again, that h on the bottom, that difference between the two x's is our h value. This formula is simply the slope formula. Can you use the slope formula to find average rate of change instead of this? Sometimes you can, yeah. But if you didn't understand all that, it's okay, because here's what I want you to get out of it. What is this x and what is this h? H is simply, if you're looking for, let's do an average rate of change from 2.3 to 4.7. Let's say that's 2 points on your graph, and I want to find the average rate of change. What is my h value? Going back to this graph, h was the distance from your original x up to your second x. So h would be the difference between 2 and 4. That makes sense. From 2 up to 4. Your h value for these 2 points would be 2. And that's really all you need to know. Well, and the original x would be, that in that case, 2. So your h value would be positive 2. Your x value, since it starts at 2, would also be 2. Well, what if we started at this 2? Or at this x? Will we get the same answer? Sure. Just make sure if you're going to use this as your original x that you use negative 2 as your h value. Okay. Let's work a problem to where we actually have to do that. Find and simplify the difference quotient for this. And I want to go a step further with this. I want to give you 2 points. 9, 3 and 16, 4. I want to not only find the difference quotient, but I want to find the average rate of change from this point up to this point. Guys, there's a much easier way of doing this. y2 minus y1 over x2 minus x1. I think the average rate of change would be 1/7. Okay, but I just want to go and show you that this difference quotient, this formula for the difference quotient, can also be used to find the average rate of change. This one's pretty nasty. G of x plus h, now this part's easier, is the square root of x plus h. Not too bad there. So we now have g of x, and we have g of x plus h. Our difference quotient formula says g of x plus h minus g of x all over h. That's your answer. Yeah, not a whole lot you can do with that. A lot of people, what are they going to try to do? They're going to try to cancel those h's. Please, I'm begging you, do not cancel those h's. There's two reasons that you cannot cancel those h's. Reason number one, the top of this fraction has two pieces. It is a binomial. If you cancel these h's, then you're saying only the first part is being divided by h and not the second part. So really, this is a distributive type situation. You can't cancel this h or divide this by h and not divide this by h. That's one reason you can't. The second reason you can't, the h on top has a square root over it. Actually, there's three reasons. The h on top has a square root over it. The h on bottom does not. Okay, it's kind of like canceling something in something in parentheses with something that's not a parentheses. So again, that cannot be canceled. And again, you see that you have kind of a parentheses situation, x plus h. You can't cancel just part of that, x plus h, with that. So for now, I don't care if you leave it like this. Now let's go back to this. This is our difference quotient. If you want to check and see if I was right a while ago about what I was saying, to see what the average rate of change, we'll call it an arc, the average rate of change, you take your beginning h or beginning x value, which is 9, and the amount of change, which is 7. So from one x to the other x, your h value would be 7. That's how much your x's change. That's your, if you want to think of it as this, that's your delta x. Delta is a rate of change. Delta x would be 7. That's how much your x has changed. And let's plug that in. Your original x plus the amount of change minus the original square root of the original x all over h, which is 7. That's your amount of change. That is the square root of 16 minus the square root of 9 over 7, which is 1/7. So this is kind of a fancy slope formula. That's pretty much what it amounts to. That is the formula for a slope, where x is your original x value, h is the amount of change from one x to the next. I do point this out that in this slope formula, you don't have to use the y values at all. Although you did kind of find the y values when you did this and that. But you see the connection between this and slope, hopefully. Okay, back to it. What you have found on the previous few problems, and your book's not going to go this deep into it, but I'm going to go ahead to make my life easier after Christmas, because you'll have at least seen it before. On the last few problems, we have found an average rate of change. The way that we did so was by finding, again, the difference quotient. And that average rate of change gave you a formula that you could use pretty much to find the slope of that secant line. Why do we need that formula? Because honestly, can't we just find the slope? Yes. So really, do we need that formula at this point? No, absolutely not. So why do we even present that problem to you? Secant lines honestly aren't that important to us. Secant line gives you an average rate of change. Let me actually rewind that and take two other points. Secant lines give you an average rate of change over 2 points. Like if I pick this point 2, 0, and this point, let's see, where's another? Right there's one. 4, 1, 2, 3, 4, 5, 6, 7, 8. 2, 0, and 4, 8. What I just did allowed you to find the secant line connecting those 2 points, slope. What if I'm not interested in an average rate of change? But I want to know how fast. This is a graph. Let's say this is a graph of you're traveling in a car, and I want to know at an instant, not an average rate of change, not an average speed, but I want to know an instantaneous speed. That's when you get into calculus. We're not looking for a speed over an interval. We want to know the speed at this exact instant. Here's how you find it. See if you can picture this. I told you that h was the distance from one x to the next x. And so in this case, between these two, your h values will be 2. Picture this. Picture your h value getting smaller and smaller and smaller. This point getting a little bit closer. You got a secant line there, getting a little bit closer again, a little bit closer again, a little bit closer, and a little bit closer. So h pretty much turning into what number? And a little bit closer. 0. Thank you. H is going away. That makes sense. So h getting smaller and smaller and smaller. So the distance between the first point and the second point is pretty much non-existent. All of a sudden, that secant line, because start connecting those dots, your secant line turns into what is called a tangent line. These secant lines, because again those lines keep going, I just connected the dots, but those lines go forever. Those secant lines that you're connecting, all of a sudden as that h value gets pretty much one on top of the other, that secant line has now turned into what's called a tangent line. It's like, oh, well, that's easy. So to find the slope of a tangent line, we just plug in 0 for h, right? Guys, go back to that formula. Can you just plug in 0 for h now? H is on the bottom of a fraction. With slope, you can't have a 0 on the bottom of a fraction, so what are we going to do? In calculus, we have this thing called a limit. And more than likely, this will be like bonus on your next test, so that's the reason I encourage you to watch this. We have what's called a limit. Not lemon, but limit. Sometimes our values can't equal a number, but it can approach it. It can get closer and closer and closer. And that's what's actually happening here. We can't just flat out plug in 0, but we can analyze this thing and say, okay, the slope of my secant line here was, I don't even know what it was, 1, 2, 3, 4, 5, 6, 7, 8 over 2. The slope of the secant line from here to here was 4. And maybe as we moved a step closer, the slope turned into 3.9, and then 3.8, and then 3.7. So as we get closer and closer and closer to 0, we can analyze these slopes and see what value are they getting closer and closer and closer to. And whatever that value those slopes are approaching would actually be the slope of that tangent line. Now I told you that we can't just flat out plug 0 in because all of a sudden you have 0 on the bottom of the fraction. So how do we do this algebraically? Let me show you. Like I said, this is going ahead and getting you ready, and a lot of you are saying, but I'm not going to take calculus. No, that's the reason. Like I said, I'll give it to you as bonuses on this test. It's the same material. Okay, it's the exact same material. You're still finding a difference quotient. But a difference quotient with a limit attached to the front of it, here's how this would actually write. You would have, instead of this, you would have the limit of this same problem as h approaches 0. That's LIM. And this would be your slope. I'm going to put slope of tan. So m with a subscript tan. That's the slope of the tangent line would be not the square root of x plus h minus square root of x over h, but that same thing as h gets closer and closer and closer to 0. Now watch how I work this problem out. I can't just plug 0 in. I want to know what happens as h gets close to 0. I can't just plug 0 in. What you could do is just start plugging in numbers that are really close to 0. Like take this and plug in 0.1, 0.01, 0.001, 0.0. let's not do that. Okay, watch. Go back to the previous problems before we work that one. Look at this one. On this problem, if we're looking for an instantaneous rate of change, if we're looking for the slope of the tangent line, what happens as h goes to 0? Well, watch. That does. It goes away. In some problems, the h just goes away. As if h gets closer and closer and closer to 0, the whole thing gets really close to 2x minus 2. Well, what does that mean? Take that same graph as before. That was x squared minus 2x, which I think is this one. And you get, I'll tell you what, this will make things easier. There we go. We got 2x minus 2 as the slope of a tangent line. Take any x value. Let's take this one. What's the x value there? Help me out, Allie. What's the x value right here? 2. So do you know how to find the instantaneous rate of change there? Plug that x in right here. 2 times 2 is 4, minus 2 is 2. If you took and drew a tangent line here, it would have an instantaneous rate of change of 2. You see that? Slope is rise 2, run 1, rise 2, run 1. Let's take another point and try it again. Here's one. Avery, what's the x value here? -1. So plug a -1 into here, and what do you get? So it should be down 1, 2, 3, 4, and over 1, right? Or up 1, 2, 3, 4, and left 1. That would be the instantaneous rate of change. So at that point, my slope of my tangent line is -4. So what you're doing with this whole difference quotient thing is you're finding a formula that you can plug any x value from this graph into that formula, and it tells you at that particular instant what the slope of the tangent line is at that point. Okay, so let's go back to our whole, the one that's going to be a little bit tougher. Because I can't just plug in 0 for h. I can't just take the h away. So watch this. Here's your trick. Remember rationalizing numerators to where you had like 5 over 2 plus the square root of x? Now let's do 2 plus the square root of 3, just to make it more real. Remember how we got that radical off the bottom? In order to remove a 2 plus the square root of 3, what do we multiply top and bottom by? The conjugate, 2 minus root 3. Top and bottom. We're going to do the exact same thing right here, to the top. This was called rationalizing the denominator. Here we're going to actually rationalize the numerator. Plus root x, and this will be the last problem we'll probably have time for. Square root of x plus h plus root x. Take good notes, guys. So that turns into the square root of x, and you're thinking, how in the world are you going to multiply that out? That's terrible. No, it's actually pretty easy. First off, they're conjugates. So all you have to multiply is your first terms together and your last terms together. A square root times itself simply removes the square roots, leaves you with x plus h. Minus a square root times itself simply removes square roots. Right? Now on bottom, don't distribute that, and I'll show you why in just a second. H times root x plus h plus root x. On top, x cancels with x and leaves you with simply an h. On bottom, you have h times stuff. I'm going to erase this. H is, these are two separate terms being multiplied, so in this case you can cancel your h's. Because that h term is in essence kind of factored out, and you're left with 1 over the square root of x plus h plus the square root of x. Now this, guys, this is still the difference quotient. This and this and this is the exact same thing, except for this one's been kind of cleaned up a little bit. But anytime you want to turn an average rate of change into an instantaneous rate of change, take the h out. Now you can do it. You'll see that you changed it around just a little bit. Now you can just plug in 0 for h. No problem. So you have 1 over the square root of x plus h, or the square root of x plus 0, plus the square root of x, which is actually 1 over 2 root x. That is not the average rate of change, that's the instantaneous rate of change. Also known as a derivative. The entire course of calculus is based on 3 premises: limits, derivatives, and integrals. You just got your first taste of what a derivative looks like. And if you took this formula along with, while you're writing it down, let me graph that. That was square root of x simply. So square root of x. There's the graph. Let me again snip that. And paste it. I have no idea what pasted at the top. There we go. Again, instantaneous rate of change. How quickly is your graph changing at this point? And you can picture that that tangent line. We're simply looking for what is the slope of the tangent line, and when x is 4, you get 1 over 2 times the square root of 4, which is 2. 1 over 4, which would be 1, 1, 2, 3, 4. That's the slope of the tangent line at that point. It's hard to draw. A tangent line, simply, it just skims it. So how quickly is the graph changing at that point? For every 1 that the x changes, the y changes 4. So it's not changing very quickly. Now here, you see your slope of your tangent line be a whole lot steeper. It's changing more dramatically. Okay, as it's a gradual slant, your graph is changing more dramatically at this point than it is this point. Not the